Today's lesson focuses on aromatic compounds. There are many different kinds of aromatic compounds, and we are going to look mostly at the molecule of benzene. Aromatic compounds have very specific structures associated with them. They are a class of hydrocarbons that have a lot of stability, even though all of these compounds have an unsaturated system, meaning that they have one pi bond, more than one pi bond, several pi bonds. So here's an example of a whole pile of aromatic compounds. And so what you'll notice is that they're ring structures, so all of them are always circular in shape. And you'll notice the presence of pi bonds or double bonds in these molecules. Sometimes you'll see some nitrogen, sometimes you'll see some oxygens. And then what happens is these molecules, so pyridine, as an example, pyridine is that base structure. And then from there, you can add on all kinds of branches and change the properties of these molecules. So these structures right here, you'll probably be exposed to later on in university if you take organic classes. But as a basic, entry point for aromatics, we are going to look at the molecule called benzene. It is extremely common, and you will see benzene ring structures in many, many, many compounds that are familiar to you even at home. Once you start putting branches on, it becomes a very widely used molecule. So benzene was first isolated by the gum, like the sticky gum that came from balsam trees. And what they did is they took those gums, or these resin gums, and they distilled them. Okay, so they boiled them off, and they noticed this molecule of benzene present in these resin gums. And the reason that they're called aromatics is because of their aromas. Okay, so they have quite a fragrant smell. And this is where that term comes from this original point of the balsam tree. The benzene structure is very specific. It has 6 carbons, and every second carbon has a double bond on it. So every carbon here has already used up 3 bonds to the neighboring carbons, and so there's only 1 hydrogen left over. This is our line structural diagram that we tend to show for benzene. So the chemical formula for benzene is C6H6, and the pi electrons that exist in the ring structure have the ability to move around. So if we look at this structure right here, what will happen in this molecule is that these pi electrons will flip around to the open spot beside them. And then from there, those pi electrons will keep moving and rotating in a circular fashion. And there's constant motion within the ring structure. Okay, so because there is constant motion, those pi bonds are actually shielded by the sigma bonds in the ring structure. So whereas typically pi bonds are very reactive and circle sigma bonds, in benzene in particular, so benzene is unique, those pi bonds circle within the ring structure, okay, so circle within, and are actually shielded from other reactant molecules. The benzene ring is incredibly, incredibly stable. Okay, it is almost impossible to break those pi bonds within the structure. So because there's constant motion, oftentimes we draw a benzene ring like this structure right here, where we have a circle in the middle. And that circle is implying the movement, constant movement of those pi bonds. The term resonance is used here, and that is because the benzene ring can exist with pi bonds on alternate carbons like that, or, and we use a double arrow to show resonance, they could be placed on just the other carbons and just move them around, one carbon within the ring. So that's what the term resonance means. So an interesting thing to note is that the benzene molecule on its own is incredibly toxic. Okay, it's a carcinogen. It is not a good thing at all. And then the minute you put a branch on it, you change the reactivity or the chemical properties of it. And many, many molecules, organic molecules, are found in artificial flavorings or pharmaceuticals that you consume, painkillers, things like that. And as soon as they are branched, they change the chemical properties and they're no longer a carcinogen. So let's name some of these benzene molecules. And there's a couple of nomenclature steps because we know the basic rules now for naming organic molecules. But the parent name is going to be benzene. Okay, so nice and easy. And then any branches that you see on that cyclical structure, we name based on, ring nomenclature, okay, which we already know. So if we look at this first molecule here, all we have is a methyl group sitting on our benzene ring. I don't have to number that because I only have one. So we would call this methyl benzene. The common name for that structure is actually called toluene. You do not need to know this, but I will point it out because toluene is actually a very common solvent in many different kinds of applications. Next door, we have our ring structure, and then we have two branches. So we know that we want those branches in lowest position order, and they're side by side. So, how do we pick which is carbon 1, which is carbon 2? Remember that we use, to break the tie, the alphabetical order option, and we want the lower. So chlorine, C comes before E with the ethyl group. So we would call this structure 1-chloro, 2-ethyl benzene. If we wanted to look at another benzene molecule, here's one here. Use my ring structure. I can put some branches on like this, and then again, we're going to number them according to lowest position order. So the way that I can number this so that I have the branches in the lowest order, I think would be like this, 1, 2, 3. And we would start that way because we would want ethyl alphabetically to be lower than the methyls. So we would have, I'm going to write it over here, 1-ethyl comes first because of the alphabet, 2, 3 dimethyl, and then the parent is called benzene. There's also another way that you can label or name aromatics or benzene molecules. And this is the old-fashioned classical method. This only works if there are two branches. That's it. Okay, so on the previous examples, if I had one branch or if I had 3 branches, this method does not apply. It only works if there are 2 branches. If the branches are placed side by side like this, and R, the letter R indicates any kind of branch. So maybe 1 carbon, 2 carbons, maybe a bromine, a halogen, could be anything. When they are side by side, we use the prefix ortho to indicate that the branches are side by side. If the branches are 1 carbon apart, we use the prefix meta to indicate that. If the branches are totally opposite to each other, we use the prefix para. So for example, if I had a benzene ring that looked like this, and I had a methyl group above and below, they are on opposite sides, I could name this by saying para dimethyl benzene. And that prefix of para tells us that those methyl groups have to be opposite to each other. If I saw something like this, so there's my benzene ring, and I saw a methyl there and a bromine here, and they are side by side, then I would use the prefix ortho. And then I would list my branches in alphabetical order. So I'm going to say bromo, methyl, running out of room, so we'll put it down here, benzene. And then that prefix of ortho tells us that the bromo and the methyl are side by side.